Hey, Chemistry, coming at you with another video today. This is going to be going over some of the questions from the review guide that I gave you earlier this week, some of the more challenging questions I felt. We're going to go over them in just a moment, but first things first, you guys know that there is a test tomorrow, and that test is not going to be a traditional test. I've actually decided that I'm going to have make you guys make a video like we did for the molarity unit. I feel like that's just a better way of getting a handle on your understanding of the material. I think some of you did a really good job on the video from last time, and I'd like to see you guys actually just do a problem in front of me. Some of you did some weird things. I'll just point out that quickly here. Do not record yourself. Don't videotape yourself and then show me paper. I'd really like it where you have your phone or something like that. I don't have my phone around me right now. Oh, there it is. But and maybe have your phone up here and then show me the work that you're doing. I don't mind if your face is in it somehow or anything like that. But it shouldn't be like you in the front frame and you kind of show me pieces of paper. I want to actually see your work and you going over it. Maybe you could have a mom or dad hold up the phone and then you can do it on a whiteboard or something like that. Or if you have a tablet where you can do everything on the tablet and you can talk over that, that's great too. It doesn't matter. I just don't want to have a big old thing of your face and you pick up pieces of paper and show me. That a couple people did that and that was really really weird. So do that instead. Show me the work. I have two frames going at once with my document camera and this in front of you, so I can do this with OBS. Some of you may know what that is, but I'm a professional and I know what I'm kind of doing here. But please do that with seeing the work. I want to see your work doing this. Anyway, that test is going to be given tomorrow. I'm going to probably drop it in the folder around lunchtime or so, and then I'm going to give you the whole weekend to do the video, and then also Monday and Tuesday. It'll be due on Tuesday night. If you need some extra time, let me know that. But a couple people over the past few weeks, something's been past due a whole week, and then they email me and say, hey, can you reopen that? And they don't really give a reason. They just sort of say that. Please get things done on time. If something happens in real life, just let me know ahead of time. But a week after, that's crazy. That's not good habit. It's not a good habit to be forming, to constantly have to have things reopened and submission windows being pushed back. I know we're on a weird situation. We want to keep some propriety going on. So please get it done in time. If something crazy happens, let me know 12 hours in advance so that I can make an appropriate adjustment. But at the same time, please, you should be able to get this done in the next 5 days or so. All right, so let's go over the problems. I'm not going to go over every single problem. I felt like a lot of these were just kind of repeats of things I've done before. The review guide's key is already posted. It's in the normal folder, so if you want to check all of the answers, go ahead and do that, checking that on Schoology. But I want to go over a few of them just so you guys know what you're doing. So number 2, a lot of people ask me about number 2, and this one is a little different because you're talking about some water that is cooling instead of heating. So when something is cooling, it's losing heat. It's getting rid of its heat. Instead of taking in the heat, that's not an endothermic process. Cooling is exothermic, so we're losing heat. And so the big thing here is we're going to set up MC delta T just like normal to find the final temperature after it's cooled, but the amount of energy that the water loses is this number or that in joules, and you're going to put that in as negative because that's an exothermic process. Cooling down is exothermic, so you got to put that in as negative, and then you plug in all your numbers there, the mass of the water and the specific heat of water, and the initial temperature is 100. Final temperature is going to be 75. It's going to cool down to 75 degrees Celsius. But the big trick here is the negative. You got to know, since it's an exothermic process, cooling, that is, the Q value is negative. A lot of people ask me about number 5 as well. This is really just a classic problem having to do with enthalpy and a chemical reaction taking place here. We've actually done this chemical reaction in class a few times. This is the reaction between silver nitrate and sodium chloride, and this produces the precipitate silver chloride. You might remember that's that kind of white chalky stuff that we made in a lab earlier this year. It feels like a long time ago, I know, but we did make silver chloride, which is this white chalky stuff. Anyway, the first question is when 50 mils of 0.2 molar NaCl and 100 mils of 0.1 molar silver nitrate are mixed, The temperature begins at 24.1 degrees Celsius, and after the reaction to form AgCl is complete, the temperature is 25.2 degrees Celsius. Based on these data, is the reaction exothermic or endothermic? And justify your answer. The answer to this question is really simple. We're told that the temperature goes from 24.1 to 25.2. So that means that the temperature of the solution goes up. And so therefore, the reaction is going to be, when I say the reaction, I mean these molecules that are being formed surrounded by a bunch of water molecules. That reaction is going to release heat into the water, and the thermometers is measuring the water, and so the temperature goes up. So the reaction is exothermic. The production of the product releases heat into the water. The water absorbs that heat, so the process is exothermic. This reaction is exothermic. How do I know that? I know that because the temperature of the water went up. That's all there is to that one. Part B, calculate the amount of heat produced in joules, assuming the specific heat of the solution is 4.18 joules per gram Celsius. This one is an MC delta T kind of problem. It's pretty straightforward. We know that the reaction's heat and the water's heat are the same value, so we can calculate how much heat the water absorbed by using MC delta T. So the mass of the water is 150 grams. How do I know that? The solution has a volume of 150 milliliters, and so the density of water is 1 gram per mil, and so it's going to be 150 grams. If any of you are being pedantic, yeah, I know it won't be exactly 1 gram per mil because there's some stuff in it, but we'll just assume that it's 1 gram per mil. So 150 grams of water, 4.18 joules per gram Celsius is the specific heat, and then the change in the temperature, 25.2 minus 24.1. Do that number crunch, and 689.7 joules is how much energy is gained by the water. I'm going to flip that into kilojoules really quickly by dividing by 1,000, so 0.6897 kilojoules. And then the last question is, what is the enthalpy of the reaction in kilojoules per mole? This is kind of the last question I can ask with this one. So enthalpy kind of has this equation. The enthalpy is equal to Q, the amount of energy that the reaction either releases or gains, divided by the number of moles of reactant. And in this case, well, I guess it's always going to be this way. Whatever reactant is limiting, that's the one you're going to put down here, because you're going to run out of the product as soon as that limiting reactant runs out. So we're going to put down here the number of moles of the limiting reactant. However, in this problem, there is no limiting reactant because you have exactly the same number of moles of each reactant. For the NaCl, you have a 0.2 molar solution, you have 50 mils of it, so you have 0.01 moles of NaCl, and you have 0.1 molar AgNO3, and there's 100 milliliters of it. We'll put L for liters. And so you're going to have 0.01 moles of AgNO3 as well. All right. So it doesn't really matter which one you put under here. It's 0.01. There's 0.01 moles of each reactant. So you're only going to make 0.01 moles of AgCl. It's a 1-to-1 ratio. So I'm going to plug into my equation there the amount of heat that the reaction produced. And in this case, it's a negative value because the reaction is exothermic. So enthalpy is going to be negative. I'm going to divide that by 0.01 moles. So 68.97 kilojoules per mole, negative 68.97 kilojoules per mole. And that's the end of that problem. Some people ask me questions about number 6 and just in general questions like number 6. So we have a reaction here where sulfur dioxide and oxygen react together to produce sulfur trioxide. I'm going to pause here for just a second. All right, I'm back. I had to take care of the little child running around really quickly. She was doing something goofy. No big deal though. So we're looking at this reaction right here. Sulfur dioxide reacts with oxygen to produce sulfur trioxide. We're told the enthalpy of the reaction. And these are just going to be some standard questions having to do with basic stoichiometry with enthalpy of reaction. Remember, enthalpy is the amount of energy that is produced in one cycle of this reaction. So if 1 mole of this reaction were to occur, 198 kilojoules are going to be, in this case, actually be gained by the reactants because it's an endothermic process. So remember, that's what enthalpy means. Enthalpy means the amount of energy that the reaction either gives off or takes in per mole of that reaction. Okay. So how much heat is produced when 58 grams of SO2 react with excess oxygen gas? So we're going to be taking our 58 grams and then we're going to convert it to moles and then moles of reaction and then multiply by the molar enthalpy. So 58 grams of SO2 converted to moles divided by the molar mass and then multiply by the ratio between how many times the mole, how many mole times the reaction occurs. So once in one cycle of the reaction, 2 moles of SO2 are used. So that's the ratio between how many times the reaction occurs. 2 moles of SO2 are consumed for every 1 time the reaction occurs, and then multiplied by the enthalpy. So it's 198 kilojoules per mole of reaction. We get this answer right here, 89.6 kilojoules. 89.6. Flip over there. All right, next question. How many moles of SO3 gas are produced if 1001.9 kilojoules of energy are produced in the reaction? So in this case, we're actually going to be trying to figure out how much product is produced if that's how much energy is taken in. So we're going to go from kilojoules of energy to moles of SO3. So 1001.9 kilojoules of energy, if those are taken in, how many times did the reaction occur? So 198 kilojoules per mole of the reaction, and then we're going to multiply by the ratio between the mole of reaction and the number of moles of sulfur trioxide. It's again a 2 to 1 ratio. So for every 1 time this reaction occurs, we get 2 moles of SO3. And so do the math there, and we get 10.12 moles of SO3. Same kind of question, just taking it to grams. What mass of O2 is necessary to generate 345 kilojoules of energy? Well, 345 kilojoules of energy, same thing, we take that from kilojoules, pure energy. How many times did the reaction occur? Divided by the enthalpy, and then multiplied by the ratio between oxygen in this case and the reaction. It's 1 to 1, so every 1 time the reaction occurs, I use 1 mole of O2. And then lastly, multiplied by the molar mass of oxygen, 32, we get 11.02 grams of O2. Okay, and then number 7 is very, very, very similar. All right, next few questions have to do with phase changes. I'm kind of just going to go through these really quickly. They're not too hard in my opinion. You just kind of have to understand what's going on there. And hopefully you've looked at my pictures and my drawings and my diagrams and the videos I've been posting. But phase changes, I'll just do number 2 here. Describe what is happening during a phase change and how are the molecules moving or changing. The big thing here to remember in a phase change is that the intermolecular forces of the compound are breaking. So remember that water is a solid, the water molecules are stuck together, they're locked into a crystal formation, and then as the water is heated and liquefied, those water molecules start to separate from one another, and then they can slide past one another, but they're still attracted to one another, and so they don't completely separate from each other. That's what the liquid phase is going to be. So a phase change is where the intermolecular forces keeping the water molecules or whatever stuck together starts to break. You're adding more and more energy, breaking that intermolecular force between the compounds. And that's really just the big thing to remember. Here's a heating curve. The heating curve, the big thing here is that the horizontal lines indicate either melting or boiling. Remember that when you phase change, you're no longer heating the substance in terms of its temperature changing. You're actually just adding enough energy at the molecular level to break those intermolecular forces. So the horizontal line here indicates melting. The horizontal line here indicates boiling. Why is the boiling line so much longer than the melting line? That's something for you to remember. It's important because remember that with boiling, you are completely breaking the intermolecular forces. The water molecules are no longer attracted to one another. Well, they're still attracted to one another, but there's the amount of energy going in to those water molecules is so much that the kinetic energy is going, making them move around so much they are no longer going to stick together, and so it's going to be gaseous. So you need a lot of energy to do that. You see on the y-axis or on the x-axis is heat added. To boil something, you got to add a lot of energy to completely break those intermolecular forces. These parts, the vertical lines, the lines going up, those are heating portions. Heating meaning you're changing the temperature. Boiling point and freezing point changes. Big thing to remember here is that when you make a solution, the solution's boiling point and freezing point are going to be different different from the pure solvent. So if I add a bunch of salt to water, that is going to change the freezing point and the boiling point. It's going to lower the freezing point and it's going to increase the boiling point. So in order to freeze something, I'm going to have to take more energy out than normal. That's why we add salt to the road. When we add salt to the road, the snow or the ice, it has a harder time freezing. And so it has to get colder and colder to do that. And if you've got a lot of salt, it's going to have to get really, really cold before it becomes ice. With boiling, you have to add more and more energy to cause those water molecules to separate from each other. So what's really going on here? When salt is added, why does it reduce the freezing point? Why does it increase the boiling point? Remember that you've got like sodium right here. Sodium is positively charged. So with freezing, these water molecules are attracted to the sodium. The oxygen side, which is negatively charged, is attracted to the sodium's positive charge. And so in order for these water molecules to condense and form into a solid, you have to take even more energy out because that sodium is kind of blocking the waters from binding together and getting into that crystal formation. In the same way, if you want to boil this sodium ion it's attracted to the water molecule. So the water molecule and the sodium ion have a strong intermolecular attraction to one another. So you've got to add even more energy in order to break that attraction now. And the water molecules are still attracted to one another. So you've got more forces of attraction that need to be broken in order to cause these water molecules to separate completely and then cause them to boil and then go into the gaseous phase. So that's really the big idea with boiling point and freezing point changes. The last question, which I don't think is actually on the key, is something I just want you to think about. Magnesium chloride or sodium chloride, which of those is going to have a greater effect on the freezing point and the boiling point when you put that into a solution? Think about this. When you add sodium chloride into water, how does it ionize? It ionizes into two ions. You got sodium ions and chloride ions. Magnesium chloride, how many ions are you going to get? Well, if you balance it properly, you're going to get 2 more, or you're going to get 3. So you got 2 ions here, and you got 3 ions here. Think about that. In this case, you've got more ions that can cause attractive forces to the water molecules. So magnesium chloride is going to have a greater effect on the freezing point and boiling point because there's going to be more ions in solution that are going to allow the water molecules to stay attracted to them and therefore have a harder time escaping from each other or harder time condensing with each other. That's the big idea with that question as well. All right, so tomorrow's test question will be up on Schoology, probably around lunchtime or so. Let me know if you have any questions, and I'll see you guys, well, office. I'm going to be doing some office hours next week. I'll get more information about that. So if you might actually see me in real life. I don't know. Have an excellent day. I'll talk to you later. Bye.